Hi, in this video we will introduce the notion of dimension for subspaces. We'll see how this notion is related to bases, and we will see some examples for dimension. Well, let me start with this question, that what is common among all the bases for a subspace? So as you know, if you have a subspace, you will have infinitely many bases for that. What is common among all these things? Well, the first thing you may say, okay, they may have some good vectors, but look at R2, for example, 1, 0, 0, 1 is a basis, and you can have 1, 1, and 1, negative 1 as another example of basis. And when you look at the vectors, oh, these are just random. There's no relation between these two bases. What is common among all these two bases and all the other bases for R2? There is nothing common but one and only one number. The theorem says every two bases for a subspace have the same number of vectors. The vectors themselves, these are crazy. They are completely random if you look at the vectors of different bases, but the number of vectors on all of the bases for one subspace is going to be the same. So if you make a basis which have 10 vectors, any other basis for that same subspace is going to have exactly 10 vectors. Not more, not less. So that number, as the mathematicians like to say, is the invariant of the set of all bases. And that is why it is important. And we call it the dimension. The number of vectors in a basis for a subspace S is called the dimension of S, and we denote it by dim S. Well, this is only one basis, but we know that all other bases going to have the same number of vectors. So dimension for a subspace is a well-defined notion. Well, let's see some examples. For example, okay, let me paste these examples here. For example, Rn. Well, give me a basis in Rn. The standard orthogonal vectors. Well, 1, 0, 0, 0 all the way 0. Then you have 0, 1, 0, 0, 0 all the way. And then the last one is 0 goes down 0, 1. How many of these we have? Remember, we call this one E1, E2 up to En. And this is a basis for Rn. And how many of those we have? There are n of them. So dimension of Rn is exactly n. Or we know that every line passing through the origin is a subspace. What is the dimension of that? Well, you know that such a line can be explained or can be described by an equation, vector form equation like this, with direction vector which is non-zero. Then you can take that vector which is non-zero, that's why it is linearly independent, and then it generates all the vectors on that line. So that means this is a basis for the line. And well, how many vectors it has? Just one. So dimension of that subspace, let me call it L, is going to be equal to 1. And for the plane, you have x equals to 0 plus su plus tv, which we know that u and v are not parallel. And that implies right away that u and v form a basis. Let me call that P, and just count how many elements it has. So dimension of the plane, that specific plane, well, is going to be equal to 2. And as you can see in these two examples, the dimension that we just defined using the linear properties is in match with the geometric dimension of those objects. Line is one-dimensional, plane is two-dimensional object, and those are the same one. Okay, how about dimension of row space? So for example, this matrix is given and you have row reduced echelon form of that given also here. Then we are looking for dimension of row space of A. Remember, the dimension of row, the basis for row space is set of all non-zero rows of the row reduced echelon form of that matrix. Here there are 3 of them, so every basis of row space is going to have 3 vectors. That means that the dimension of row space of A is 3. How about a column? So what do we do for basis for column? You just go pick the basis, the columns related to the columns in the row reduced echelon form which contains leading one of some of the rows. Here in this case, then that means that dimension of column of A is equal to 3. How about the dimension of nullity, or dimension of null space of A, sorry. In this case, well, you can solve the AX equal to 0 and you will see that this column and that column will be free variable. So the variables for these column, these two, so you need a variable, free variable st, and when you write the equation or the solutions of the homogeneous system in terms of st, the coefficient of s will be a vector and the coefficient of t will be another vector. These two are going to be linearly independent and they're generating the whole null space. That means that the dimension will be to the dimension of null space of A. So we will learn more about the dimension, row space, column space, and null space of matrices in another video. But as an example, now you know how this works. Just count the number of vectors in one basis. That's the dimension.